we are going to discuss example 6. Basically, it's just an example of showing you how to perform scaling and reflections consecutively on an function. So just look at, for example, the example A. Here is an example of compressing a function horizontally by a factor of 2. After that, you have to make a reflections across the y-axis. So we are going to demonstrate to you how this could be done theoretically. So you have a function of y. So here the function have an expression of fx. According to the formula, here is equals to x power 4 minus 4x cubed plus 10. 4 minus 4x cubed plus 10. So the first thing you want to do is to compress the function horizontally. So remember, the compression of a function horizontally is obtained by replacing the values of x in the argument of the function by, if it's compressed, then you have to multiply it by the compression factor of k, so that the function of y would then be cast into another function of y1, where y1 is the compressed version of the original function, and y1 is obtained by replacing the x in y by kx. And here the y is this expression, so you would replace all the x in y by kx minus 4 kx cubed plus 10. Here the k is taken to be a factor of 2. So you have an expression for y1 that should represent the compressed version of the original function by a factor of 2 horizontally. So y would then be reflected into the function of y1. So that is the first part of the operation as instructed in example A. So once you have compressed the function horizontally by a factor of 2, then you want to make a reflections on the function y1 about the y-axis. So that is to say you have to then make the y1 to be reflected. So you have a function of, say, y equals to fx. Then say a function looks something like this, but it's reflected onto the y-axis, then the function will look something like this. And the operation of carrying out the reflections about the y-axis is by replacing x by minus x. So under this operation of replacing x by x, then y1 would be brought to another function of y2, where y2 is obtained from y1, where the argument of x in y1 is to be replaced by minus x. So you can then find out what is the expression of y1 from this expression. Okay, so here if you replace all x by minus x, then you get x2, which is equals to k times minus x power 4 minus 4 k power 3 minus x power 3 plus 10. So you simplify this expression, you would get the expression for y2, which is an reflected versions of y1 about the y-axis. So this can be obtained by carrying out the operation using Mathematica. So before we show the results or the operation using Mathematica, we first look at what the questions looks like and what's the answer. So this is original function of the function f. Then after making the compression about the y, about the along the x-axis, compress the functions horizontally by factor of 2, and then reflect it about the y-axis, that is the function you finally obtain. Okay, so it's a two-step procedure. Let us implement this procedure one by one using Mathematica. So I have already prepared a code for this. Okay, so this is the compression function. Originally, the function is x power 4 minus 4x cubed plus 10. Then I define the compressed version of the function y1, which is obtained by multiplying the x with the compression factor of k. So each k is x in the original y function is to be replaced by kx. Once I have done that, that would be the expression for y1. y2 is the curve obtained from y1 by reflecting it about the y-axis. The reflection about the y-axis is to replace all the x argument in y by minus x. So this is the original graph. This is the graph that is obtained by compressing the original graph by a factor of 2 along the horizontal direction, and this is the final curve obtained after reflecting y1 about the y-axis. Okay, so when you press the button, this is the graph that I obtained. You can compare the shape obtained by Mathematica with the graph obtained by the PowerPoint, right? So here, let me try to drag my screen so that you can compare it better. Okay, so more or less you can now make a comparison. So the graph that's obtained by Mathematica is this. So this is the original curve, the blue color curve, which is displayed by here. So this is exactly the original function. So the original function y is then compressed into y1. So y1 is this function, which is an horizontally compressed version of the original function, which is in blue color. Then this function of y1 is reflected about the y-axis to result in a curve which is green in color. So this is the resultant functions after the two successive operations, and this curve of green color line is just exactly the same as this one. Okay, so the expression for the final curve after the two-step procedure is just given by y2. And if you want to know what is the expression of y2, you just ask Mathematica to print it out for you. So this is y2. So the expression is given by this. Okay, so the y2 expression is 16x power 4 plus 32x cubed plus 10, which is exactly as the one that is given by the solution here. So once you have understood the operations in example A, then you can easily reproduce the operation B. So operation B is a slightly different operation where you have to compress the graph vertically by a factor of 2, then reflect it about the x-axis. So let us try to implement this in Mathematica. But before that, let us try to revise what is the operation that needs to be done to compress the graph vertically by a factor of k. So the way how you do the vertical compression, if you still remember the previous lecture, this is obtained by replacing all values of y by a factor of k. That amounts to compressing a graph vertically. That operations will land on a new function. I call it y3. And y3 is a function obtained from y by replacing y by a factor of k. So this is just simply equals to y divided by k, where k is, in this case, the compression factor of 2. Once you obtain this compression, the question asks you to make a reflection across the x-axis. The operations to reflect the function across the x-axis is graphically represented by this situation. If you have a function like this, when you reflect it about the x-axis, then you get this graph. So if this is y equals to fx, then the reflected version of it, which I call y4, is just equals to minus f of x, where you just replace every single value of y by minus y. Okay, so this is operated by replacing y3 by y3 times minus 1. So under the operations, y3 is brought to y4, which is the reflected version of y3, where y4 is just equals to minus y3. And what is minus y3? Minus y3 is just equals to minus y over k. Right? So that is the expression for the reflected version of y3, where y3 is the compressed version, vertically compressed version of y. Okay, so that is the theoretical part of the function. So this is the original function. After you have compressed it vertically and reflect it about the x-axis, that is the result that we expect to obtain. So let's just see if we can reproduce this graph using the operation of Mathematica. So here, to obtain the graph, let me go back to my function here. This is the original functions of y, and I'm going to construct y3 and y4. So the construction of y3 is that the y3, according to my explanation here, is just divide the function y by the vertically compressed factor of k. So y3 is just equals to y of k divided by k. So that should compress the function vertically by a factor of 2. Then y4 is the vertically reflected versions of y3. So we have y3, then if you were to reflect y3 about the x-axis, you just multiply by a factor of 3. So that y4 should give me the reflected versions of y3. So here I'm going to plot y3 and y4, and I have to adjust my range so that I can compare it with the function here. So the function should be running from minus 1 to 4. Okay, so I'm going to run it from minus 1 to 4, and the range to be plotted is from minus 1 to 4, and the vertical axis should display from, say, I think minus 11, I let it to be minus 11 up to positive 10. So I expect this graph to be similar to this one. Okay, so this is the original graph, the blue color graph. The blue color graph is the original function. Then y3 is the vertically compressed version. So this graph is obtained by compressing the original functions to a factor of 2. So this line is the compressed version of this blue color line. Once you obtain the y3, then we will reflect the y3 about the x-axis, so that this orange color curve is now reflected about the x-axis to give you the green color curve. So the green color curve y4 is just this curve as displayed in a PowerPoint. And if you want to know the expression of y4, ask Mathematica what is y4, and the answer is this expression. So this expression is the same as here, right? So it is so you compare it, then it's minus half of x power 4. So here you have a factor of have a factor of minus half power 4. Then you have 2x power 3 times 2x power 3. So this is 4x power 3 times 2. So this is really a factor of 2x power 2. Then you have a minus 5 here, which is the same as the result that is given by the PowerPoint. So with this, we complete the examples of of 6, where we perform consecutive scaling and reflections operations onto a given graph. So the conclusion is that for this topic, you can perform various types of operations onto a given function. So you can add two functions, subtract, divide, multiply the function by a constant. You can also form composite of functions. You should be able to reproduce a graph after you have carried out all these operations on the functions. Apart from that, we also discussed in this topic how you could perform scaling on the functions and shifting the function vertically up or down and reproduce a graph of this shifted function. Then when you compress or stretch the function, you can do it along the horizontal direction and vertical directions. So you should be able to tell and know how to reproduce this stretch or compressed graph, whether it is along the vertical or horizontal directions. And you should be also able to obtain the resultant functions under such operations. Okay, so that's all for this video. Thank you for your attention.